Hello everyone, today we are going to talk about joint resistance and joint heat dissipation. Today, we'll cover 4 key topics to explain the concepts in this lecture. First, we'll examine the several types of joints used in the construction of superconducting magnets. Next, we will discuss the heat generation at these joints. Following that, we will delve into the specifics of superconducting solders. Finally, we will explain a persistent currents mode in superconducting magnets, which are essential for their continuous operation without power input, especially in MRI magnet. In the field of superconducting magnets, the techniques used to create joints are identified by a variety of names. On the left, it is classified based on the joint structure. This categorization helps us understand how each joint type is constructed. On the right, the classification is based on the direction of the current after passing through the joint. In addition to the types listed on this page, such as the bridge joint, there are numerous other techniques known by various names in the field. During the process of joining superconducting wires, a small amount of resistance typically develops at the joints. This resistance is a significant source of concern, as it can lead to heating issues. Many of the problems associated with superconducting magnets originate from this very aspect of the joint process or from the heat generated at these joints. Consequently, there is a critical need to determine the optimal conditions for joining superconducting wires, including the best temperature and duration for the process. As of now, extensive research is still required to establish these parameters. Next, we will explore the concept of superconducting solder. The idea of using materials that possess superconducting properties as solder has been an area of research for some time. Persistent current mode is crucial for applications that require superconductors to carry current indefinitely without power dissipation. Achieving effective superconducting junctions that can support this mode involves innovative techniques and extensive research. Significant progress has been made using materials like NBTI, where pressure is applied to create junctions between superconducting wires. Another approach involves connecting wires to MgB2 powder to form superconducting junctions. Currently, researchers are also exploring the creation of superconducting junction between different types of superconducting wires or Rebco superconducting junction. Currently, MRI machines utilize shorted superconducting loops to implement a persistent current mode. First, a heater is activated within the system to temporarily disable the shorted superconducting loop. Next, the magnet is charged by supplying current from a power supply. This current energizes the magnet to the required field strength. Once the magnet is fully charged, the heater is turned off, allowing the shorted superconducting loop to become active. At this point, the loop carries a persistent current, meaning it can maintain the current without any additional power input. In summary, the term joint refers to the connection between two separate superconducting wires. There are various methods and terminologies associated with joints. Next, joint dissipation refers to the heat generated at the joint after the connection is made. In superconducting magnets, which operate at extremely low temperatures and carry large currents, accounting for joint dissipation is critical. Superconducting joints are among the most important aspects of superconducting magnet technology. Many issues in superconducting magnets arise during the jointing process or as a result of the joint itself. Therefore, this remains an active area of research, with ongoing efforts to improve joint performance and reliability.